time. Friday do 6 to 5 Monday through Friday, and then I got 7 on Saturday. Might be. So might be 6 more.
That's a lot of hours.
Right.
There you go. All right, today we are going to talk about natural logs. So this is going to kind of serve as a review of things that we've already talked about, while also introducing one small new idea. Okay, so E, we're going to talk about the number E today. Okay, the number E. E is a number now. And it's an irrational number. What does irrational mean?
It's an ugly number.
It's an ugly number. Yeah.
It's like a decimal.
It'll be a decimal.
Some fractions, I think.
Not pi.
Pi is an example of an irrational number.
Is it some fractions?
Well, an irrational number is a number that cannot be written as a fraction. Okay? It's a decimal that goes on forever, that doesn't repeat. Therefore, it cannot be written as a fraction.
What?
That's what an irrational
How does
number
it go on forever and not repeat? It don't make no sense.
Well, like pi. Think about pi.
You said repeat.
Yeah, if you a repeating decimal could be something like 0.898989, right? It repeats over and over. An irrational number like pi or e is something that doesn't
It's
repeat.
just a bunch of gibberish.
Right, like pi is 3.1415 blah blah blah. No part of it ever repeats. Okay, it's just. It seems like a collection of just random numbers. It's not random, but it seems that way.
I tried to read pi to the million one time.
Wait,
I tried to read pi to the million.
it'll take a really long time.
Yeah, I halfway through.
You got halfway through? Oh,
I
you got
don't
halfway
have-
through.
I got like 5 lines in.
Alright, so the approximate value of E is 2.718281828.459. So it kind of looks like it's going to start to repeat, and then it doesn't. Alright, 2.718281828.459, and then it does actually continue on forever. Right, so if you want to put a couple of dots there to show that it continues on forever, you can, but this is the first few decimal places of our number E. Okay, E actually shows up in a lot of applications, and hopefully we'll get to the biggest application. Okay, it shows up a lot in money and banking, but it does also show up naturally in nature sometimes. Right? Euler. Right, this guy's name is pronounced Euler, not Euler.
E-ruler.
Euler. Okay. Euler is the one who discovered this. Okay. He was actually brilliant. He's not stupid.
Come on, can't you spell his own name right? Sounds like Euler.
That's his last name. His first name is Leonard. Leonard Euler. Okay, so this is our number E that we are going to start taking a look at today. So first, okay, let's take a look at exponential functions with base E. Right? These are called natural base, okay, because E is the natural number. So a simple example of this would be like e to the x equals 10, right, where E is the base of the exponential. What we're going to focus on more today, though, are natural logs. Okay, a natural log is a log with a base of E. Okay, a log with a base of E, and these are called natural logs or natural logarithms. So, an example of this, we would say log base E of 7 equals x, right? Something like that. Now, when we write log base E, generally, you're not going to see it written like this. Okay, you're not going to see base E. What you're going to see is an abbreviation of ln. And whenever it's handwritten, sometimes it's handwritten in cursive. I usually handwrite it in cursive. Sometimes you'll just see it in print. Right? You could just see it ln. Okay, and this is log natural. Right? Instead of natural log, I believe it's French where they derived that from. So instead of natural log, it's log natural. So ln is the abbreviation that you'll usually see. So instead of log base E, what you're going to usually see is ln of 7 equals x. And when you see ln, that means log base E. Okay? When you see ln, that means log base E. So we're going to go through examples where we're converting between logs and exponentials. Then we'll go through a few examples using properties of logs, and then we'll go through a few examples solving natural logs here. So this is going to be, like I said, a little bit of a review of things we've already talked about, but now with the number E. So first, I've got these 3 examples where I've got a base E exponential function. I want to rewrite these in logarithmic form.
I still do 10 to the 10, 10 to the 10th power, and I got 1e10.
So, no, it is not actually. On the calculator, the notation there, we got 1e10. What that really means is 1 times 10 to the 10th power. This is the calculator's way of writing scientific notation. So this is what that actually means. Yes. Right. So when we're rewriting, either way, right? Exponentials into logs or logs into exponentials, we want to use the lazy 7 idea. So what we would say here, e to the x equals 24. The base of the exponential will become the base of the log. So log base e, we're going to write as the natural log, right? We're going to write ln. So log base e is ln. So we would say ln of 24 equals x. And remember, what this really means is log base e of 24 equals x. But we're going to write log base e as ln, right? Natural log. So how would I do number 2? ln of x equals 9. Yeah. How about the last one? Yep. ln of 72 equals x plus 5. Using that lazy 7 idea. So we can also go the other way, right? Given a log, we can rewrite it in exponential form. So let's take a look at some of these natural log functions. So how would I rewrite this? First one, ln of x equals 58. How would I rewrite this in exponential form?
You would start off with E.
Yeah, so we want to think that the base of this log, bless you, is e. Right? The base is e. So when I'm rewriting my exponential, the base will be e. So we do the lazy 7. E to the 58th power equals x. How about this one? Natural log of 6 equals x. dx equals 6. How about this last one?
32nd power equals x minus
32nd power equals x minus 9. Feel okay with that? All right. Let's then use our properties of logs. Okay, so these are the properties that we talked about for condensing and expanding logs. We're going to just apply these now to natural logs. So, if you remember, whenever we were adding two logs together, that meant we multiplied what was on the inside. Whenever we were subtracting two logs, we divided what was on the inside to combine them into a single log. And then whenever we had coefficients, we were able to bring those up as exponents. And all these work backwards as well. And if we have an exponent, I can bring it out as a coefficient. If I'm dividing two things inside of one log, I can split that up into two logs using subtraction. And if I'm multiplying two things inside of a log, I can pull that apart using addition. Okay, so this first set, we want to condense. Okay, I see multiple logs. I want to condense those into a single log. So if I've got the natural log of 3 plus the natural log of 16, how could I combine those into a single log?
You do ln base e, and you do parentheses 3 times 16 parentheses.
Yep. And then since these are both numbers, I could do that multiplication. Right, so what is 3 times 16?
48.
48. So the natural log of 3 plus the natural log of 16 is equal to the natural log of 48. Alright. How about this one? Natural log of 63 minus 2 times the natural log of 3. You guys take a second and see if you can come up with this one here. I brought the 2 up as an exponent. Did we get natural log of 7? Okay, so the first thing we want to do whenever we're condensing is look for coefficients. Bring that coefficient up as an exponent. So that would become 3 squared then, which is 9. Then to combine these two logs together, if I'm subtracting, I would divide what's on the inside. So 63 divided by 9, this gets me natural log of 7. You okay with that one? All right. All right, let's try another one here. Got a calculator. All right, so try this one here. Okay, both of our logs have coefficients here. So that's the first thing that we will want to take care of. So see if you can simplify this or condense this into a single log. You can cheat on notes.
Oh, yeah, sometimes that's I don't like that.
Just because of the fraction.
No, not even that.
What are you confused?
I don't even pull them. I don't know. I'm still trying to figure out.
Alright, so on this one, condense. First, want to look for coefficients, so those would come up as exponents. So I would have natural log of 64 to the 1/3 and natural log of x squared. Then if I put 64 to the 1/3 power into the calculator, that's just 4. So I get natural log of 4 plus natural log of x squared. And then if I'm adding two logs, I can just multiply what's on the inside to combine them into a single log. So 4 times x squared is just 4x squared. You okay with that? I asked you first. Alright. Then, let's go the other way. Let's expand some natural logs. So, number 10 here, I've got the natural log of 5x. How could I expand that?
ln base e to 5 and ln base e to x.
What am I doing in between?
Either multiple. Well, yeah, I guess multiple.
So I'm multiplying natural log of 5 times natural log of x.
Plus it.
You could be plussing. And whenever we're multiplying two things, we would split those up into two logs using addition. So we don't have to write the base of e, right, whenever we're just writing natural log. So I can just say natural log of 5 plus natural log of x.
Base e is like base 10.
Yeah, similar. Yeah, so if you just see like log of 5x, you know it's base 10, but you don't have to write it or say it. Alright, you okay with that one? How about something like this?
No.
Well, I got it.
My God.
I could do like 2, or the coefficient 2, I think, the ln.
So you want to bring this 2 out front?
Yeah.
We could do it that way.
I mean, or
I think it's a little less confusing for people to first distribute this exponent in, right? So whenever I've got a power raised to a power, I would distribute this exponent to every variable that we see. So first, I could just write this as the natural log of, so when I've got a power to a power, I multiply them. So a cubed to the second would be a to the 6th power. And then over b to the 2nd power. Alright, so now what can I do?
That's division. You do ln a to the 6th power minus ln b to the squared.
Right. Since I'm dividing, I can split this up into two logs using subtraction. There's one more thing I can still do.
I can just throw the 6 and the 2 out front.
Right. I can take my exponents and bring those out front as coefficients. So 6 times the natural log of a minus 2 times the natural log of b. You okay with that one? Alright, so again, this is not new information. This is stuff we've already talked about. We're just applying it now to natural logs. Alright, so on the back then, let's solve some equations. Okay, and again, this isn't new. We've already solved logarithmic equations. We're just now throwing in natural logs instead of log base 7 or log base whatever.
Would this be like logs and you just do 4x minus 7 and then you just equals 15 minus 2x?
Exactly.
And then you solve for x.
Yeah, so this, excuse me, this is type 1. This is type 1 of our log equations, right, where I've got a log equal to a log. Whenever I have that, I want to get one log equal to one log. So remember, we could have multiple logs on each side. Okay, we'll look at examples where we have that, but here we don't. Here we just have one log equal to one log. Once I have that, I can just take what's on the inside and set that equal. So I can just say 4x minus 27 equals 15 minus 2x. So then, this is a pretty straightforward equation to solve. And I could add my 2x over here, and add my 27 over to the other side. So 6x equals 42. Divide by 6. We get x equals 7.
These are
Yeah, they're going a lot faster than our calculators. So, do I have to do anything else, or is that just my answer? We have to check it, right? So we need to plug this back in wherever we see an x to make sure that we get a positive value. So in this first one, I would plug 7 in and say natural log of 4 times 7 minus 27. 4 times 7 is 28. 28 minus 27 is 1. So this would just be natural log of 1. So that works. We have to check on the other side as well. So natural log of 15 minus 2 times 7. 2 times 7 is 14. 15 minus 14 is 1. So we get natural log of 1. 1 is a positive number. So 7 is a legitimate answer. All right. You okay with that? All right. How about this one? I've got 2 times the natural log of k equals natural log of 2k plus 15.
If you put the 2 as an exponent for the k and put k squared equals 2k plus 15.
Exactly. Bring that 2 up as an exponent first. So we'll have natural log of k squared equals natural log of 2k plus 15. Now that I've got one log equal to one log, we can just say k squared equals 2k plus 15. How would I solve something like this? How do I solve a quadratic?
Could you put it, or do you want to? Could you minus the 2, bring it over and negative 2k squared equals 15?
No, because this isn't a k squared, so I'm not able to combine those. Yeah, to solve a quadratic, we want to get everything on one side equal to 0. Right? So I can subtract both the 2k and the 15 over.
How would you move the k squared?
Well, we're not going to move. We're going to leave it on this side. When we're solving a quadratic, or really any higher power equation, we want our highest power to be positive. So since my k squared is positive on the left side here, I'm going to subtract my 2k and my 15 over to keep that k squared positive. So we'll have k squared minus 2k minus 15 equals 0. Now what? How would I solve this from here?
Can't combine like
Combine like terms. You want an x factor. So I'm looking for two numbers that multiply to negative 15 that add to negative 2.
would it be 5, 3?
5 and 3.
1, I think would the 5 be negative?
5 would be negative. So since my leading coefficient here is 1, I can go straight to factors, and these would be my factors. So I can say k minus 5 times k plus 3. Now what? Do I finish solving this? Or is that my answer? Are negative 5 and 3
No,
my
it's
answer?
going to be k equals 5 and k equals negative 3.
Right. So what we want to do is set each of these factors equal to 0. So I would have to add 5 to the other side.
K equals 5 and K equals negative 3.
Right. So now I have to check both of those answers to make sure they work. So let's start with 5. If I plug 5 in here, I would get 25. Right? That's good. If I plug 5 in here, 2 times 5 is 10. 10 plus 15 is 25. Those are both positive values. They equal each other. So 5 is a legitimate answer. Let's try negative 3. If I plug negative 3 in here, what's negative 3 squared? Yeah, positive 9. Right? Negative 3 squared is positive 9, so that would work. And then 2 times negative 3 is negative 6, plus 15 is, again, positive 9. So negative 3 actually works as well. We get 2 answers that work for this problem.
So it doesn't matter that in the original it's just K?
Oh, yeah. Did skip down to that. I didn't look at the original.
How do you?
Yeah, I guess that would. Yeah, that would change that, wouldn't it? But then, because you could just use the property to bring the 2 up, or if it was like this, you could bring the property to bring the 2 down. Yeah, I guess if we're just looking at the log in the original problem, I'm just plugging negative 3 in right here, we would have a log of a negative number. So, we would say that negative 3 doesn't work.
Oh, that's really much.
That's what you want first thing in the morning, isn't it?
Let's see.
Today is Wednesday.
Oh my God, it's free code day. You hear that free code day? I'm not working, so we get to do.
How long?
Only if you're working do we get a good code.
Yeah, 'cause I'll be making a mess and big bags in trouble because they're a little heavy.
Alright, let's take a look at 15 here. So on this one, I've got multiple logs on both sides of the equation. I need to combine both sides before I can drop the logs, before I can use the one-to-one property. So first, on the left side, I'm subtracting these logs. How would I combine those? Yeah, I just divide what's on the inside. So I could say this is just the natural log of 72 divided by 4. What's 72 divided by 4? 18. So this left side would just become natural log of 18. Now on the right side, I've got natural log of 6 plus the natural log of a minus 2. How can I combine those into a single log? Multiply. And I would multiply 6 times a minus 2. So, I guess I could have written that out, write this out. So 6 times a minus 2. Right? To do that, we want to make sure we are distributing that 6 through to both of those terms. So I would have natural log of 18 equals natural log of 6a minus 12. Now, I've got 1 log equal to 1 log. Now, I can set what's on the inside equal. So we can say 18 equals 6a minus 12. Then what? What is it? Alright, add the 12 over. So we would get 30 equals 6a. And then 5. So we get a equals 5. So we want to plug that back in to make sure it works. There is only one a in my original problem. So right here, if I plug 5 in here for a, natural log of 5 minus 2 is 3. 3 is positive. So 5 works. Yay. Questions on that one? All right.
Wait, I can't see.
I had a really nice dream. I was having a dream that I was graduating already, and I wake up that, wake up! It's time to wake up! And I'm like,
Alright.
So it's a good dream.
yeah, but Tyler woke me up.
Not good to wake up.
No! And like he woke me up like half hour before I had to be up anyway. So I'm like, oh, thank you. But like, you know, I try to go back to bed and like relive that dream and like you can't. And then you just lay there thinking about how much I should.
Can't kill anybody.
No, Ali.
All right, let's take a look at this one. 2 times the natural log of m plus 4 equals the natural log of 4. How could I start this one? We could make the 2 an exponent. That would be one way to approach this. So we could say this is the same as the natural log of m plus 4 squared equals the natural log of 4. Now what? What can I do now?
Now we do.
So we know we've got 1 log equal to 1 log. So we can say m plus 4 squared equals 4 now, right? Now, we could expand this out. Now, to expand it, I can't just distribute this exponent in. And if I've got a binomial times a binomial, I'm not just going to get m squared plus 16. I'm going to have a middle term here. So I would have to say m plus 4 times m plus 4. Okay? That is absolutely one way that we could do this. Subtract the 4 over, factor it. There might be an easier way, though. Okay? This is something that we haven't really talked about much this year, but I know you did it last year, and maybe even in Algebra 1 as well. Okay? If I've got something set up like this, I can just take the square root of both sides of the equation. If I take the square root over here, I would just be left with m plus 4. And if I take the square root over here, what's the square root of 4? 2. And so 2 times 2 is 4. But there's another number when multiplied by itself, we would get 4. Yeah, by itself. So whenever we take the square roots, we need to include plus or minus, right? Because negative 2 times negative 2 is positive 4. So there are two answers to the square root of 4, positive 2 and negative 2. Now, to solve this, we can subtract the 4 over, and we get negative 4 plus or minus 2, which means we're going to have two answers, right? What this really means is we'll have m equals negative 4 plus 2 and m equals negative 4 minus 2. So negative 4 plus 2 would get me negative 2, and negative 4 minus 2 would get me negative 6. So now, we want to plug that back into our original equation. So if I plug negative 2 in for m, I would have negative 2 plus 4. That would be a positive 2, right? So m equals negative 2 is a legitimate solution because we get a positive inside of the log. If I plug negative 6 in, negative 6 plus 4 is a negative number. So that one is no good. The only answer we get here is negative 2.
Why does it say m equals negative 4 plus or minus 2?
Well, so when we took the square root of 4, we had to say that was positive and negative 2.
Okay.
Yeah, so then we subtracted 4 over, we got negative 4 plus or minus 2.
Bless you.
And we split that up into its two parts. Alright, so the last two problems that we want to look at are solving type 2 log equations, where we have a log equal to a number. Alright, so let's take a look at 17 here. Natural log of 8x equals 2. The first thing that we want to do when we have this type is to get the log by itself. Well, that's already the case here. Right? Now, once the log is by itself, I want to rewrite this as an exponential equation. How would I rewrite this as an exponential? Yeah, we're going to use lazy 7. Right? So what's the base of this log? E. Right? So what we're going to end up with is e to the second power equals 8x. Now, to get x by itself, I would just divide both sides by 8, and I get e to the second power over 8 equals x. Now, that's an acceptable answer. Okay, we have x by itself. But we could also plug this into a calculator to get a decimal.
You put an E.
So, on the calculator, Mikey stole a bunch of the calculators here, but if you have a calculator in front of you, the E button is right above division. Okay, so we would do second division to get our value of E. So on the calculator, we would do second division, and I want this squared, so E squared divided by 8. Yeah, so we would get 0.92363, like that.
Kill one.
What's that?
Kill one.
Yes. So we can just go out to a couple of decimal places. So we can say 0.92 value we would get here. Okay, so on the calculator, E is above the division button. So second division will get you the number E. Alright, you okay with that one? Alright, one more. So here I've got the natural log of x minus the natural log of 9 equals 7. So first, I want to combine these into a single log. How can I combine the left side here into a single log?
Subtractions is division, so it would be x over 9.
So we can say natural log of
Shit.
x over 9
Enough.
equals 7. Now we've got the log by itself equal to a number. Now I can rewrite this as an exponential. So what's that going to look like?
Usually 7.
Yeah, we're going to lazy 7.
E to the 7 x over 9.
Alright, so e to the 7 equals x over 9. How would I get x by itself now? If I'm dividing x by 9, I would multiply both sides by 9. So these 9's would cancel. I just get 9 times e to the 7 equals x. So that we could put into the calculator to get a decimal approximation. What would we get? Yep, that's right. 69.69. 9,869.69.